All right, let's get started. Today we're going to be talking about elementary sorting methods. These are some of our basic sorts. Going to give us a background on sorting and the way we define it, and we'll look at some simple sorting algorithms, and then we'll also look at ways to tune those algorithms. So this might be useful in your general thought process for trying to optimize some of your code as you write it and as you get to the point where it's written and it needs a little bit of updating. Okay, on our cover slide here, we have this photo of a family, and it's kind of creepy in a way that all old photos are kind of creepy. But I think the kids are supposed to be sorted here, even though I feel like the youngest boy here on the left is a little taller than his sister. But, you know, it's the thought that counts. All right. So we'll start with an overview of sorting. Like I said, we'll give a definition of what we think of as sorting, and we'll look at some of the mechanics to make sorting work, and then we'll get into our individual sorts. The task of sorting is to put some records in a sequence, and that sequence by default is ascending order. When we think of things as being sorted, we think of them in the way that we would count them. So there's natural numbers, the counting numbers, that's the ones that start at 1, 2, 3, 4, 5, because it's natural for us to count upwards. So when we say sort, we mean in ascending order, unless it says otherwise. If it doesn't say a descending sort, then sort just means ascending. That's the default. That's one of the things that's the challenge in the STL, is understanding the way that these comparators work. We talked about it when we were dealing with priority queues. There's some defaults that go into place. And the STL saves you code by saying, if you want to do all of the things that the STL loves to do, you can get by with one comparator, some minimal amount of work, and that comparator is the less than comparator. So with that less than comparator, you can sort things, which by default means in increasing order. So a less than comparator is going to give you an increasing sort, just like a less than comparator gives you a maximum priority queue or a max value priority queue, because by default we think of the bigger numbers as being more important. So those things are tied together because of the way that the STL defines them. Less than comparator means increasing sort. Less than comparator means a top down or a max priority queue, where the things get smaller as their priorities decrease. So that's one that is very important to pull together. And oftentimes when we talk about sorting, we refer to them as records. And this is just a classic way that things are done in computing. We'll also talk about files oftentimes. But a record is a group of information, related information. So stuff about a student, your student file might compose a record in a collection here, and that record might have your last name, first name, date of birth, you know, all of the information that is pivotal to you in terms of being a student at the university. So the record is the collection of data, and then the key is the object or value that's used to sort it. Early on, we'll be talking about very simple applications here where the record and the key are the same thing. So if I say, here's a collection of integers, sort them, I'm sorting those where the record is being sorted, but the only thing in the record is a single field, which is the key itself, which is that integer. Later on, when we start adding things to it, you can say, I would like you to sort all of these student records by student ID. So the record is all of the information, including the ID, and then the key is that portion of the record that is what we use to sort. And we're going to do this with respect to some operator or a functor. We see here that the operator less than is being used. So standard less will call operator less than if it exists. That's the way that it works. The STL uses standard less, and if operator less than is defined for your data type, or if you've got a built-in data type, which of course less than is also defined for, then it will use the less than to make that happen. The elementary sorts we're going to be talking about: bubble sort, selection sort, insertion sort, and counting sort. We'll go through those today. On the other side there, the high performance sorts, we've got quick sort, merge sort, heap sort, which we've already taken a look at while we were working on heaps. And then radix sort, which is another type of sort that we don't really discuss, but it's a very commonly used high performance sort, so it is mentioned here. Let's see if I can update my lighting just a little bit here, sorry. There we go, a little better. Okay, moving on. We call these elementary sorts, but they're not useless, and here's why. For one, we're going to use them as a great way to approach a problem. As we see the problem, how do we approach it? How do we get to a solution? We'll also be able to compare different ways that this gets done with these multiple solutions, and we'll start working on some optimization with each one of these algorithms. We're going to tune them just a little bit to see what we can get. And the last one we'll see with insertion sort, we'll get a fair amount of tuning there, and it's going to be pretty interesting the way that that does it. To be clear, ahead of time, when I tune these things up, when I make them faster, I will not be able to change their complexity class. But that complexity class is a big O thing, where we drop out some constants and some lower order terms. So if you want to speed something up, you use smaller constants or you reduce smaller order terms. So that's the type of work that we will be doing. So it will make things faster, not screamingly faster, but noticeably faster. Sometimes our elementary sorts are actually good enough, even though when we look at insertion sort, it's an n squared sort. The way that it gets implemented in computer programming actually makes it the fastest sort that there is for a small amount of data. So even though we've got more advanced sorts, when we've got a small amount of data, an insertion sort is actually a better idea. And that's why we talk about combining this with other sophisticated sorts. We'll take a look at intro sort, and intro sort is a combination of insertion sort, quick sort, and heap sort. So all of these sorts get worked out together to make this as really fast as it can be. And an intro sort is the standard sort that's used in the STL. So that's why we can say sometimes these elementary sorts are still good enough to be used. Which containers can be sorted? Well, we've got our standard contiguous versus connected data representations. We've got array type things and linked list type things. We're going to look at both, but we'll start with arrays. It's going to be a lot easier to sort things with random access. Some basic tasks are of course better suited for arrays, and we know that some basic tasks can be adapted to be used in linked lists. So some of these things are going to depend on how the data is represented. So that's the classic 281, it depends answer. The STL sorting is done using iterators, much like everything else in the STL. So we don't focus on the container, we focus on iterator use. And this gives us our generic programming ability to say, here's one sorting algorithm that can sort things in a deck, it can sort things in a vector, it can sort things in a linked list. We get some pretty interesting things going on there. So in order to get sort, we need to include algorithm. That's where it is. Here's a simple version of it, getting this done in the fewest lines possible. We've included algorithm. Here we've got a vector, which we didn't include, forgive us. We've got a vector of integers, A, that's declared and initialized with these 5 values, 4, 2, 5, 1, and 3. The next line is standard sort call. So it calls sort with a range, and that range is defined as the beginning of A, which is an iterator pointing at the 4, which is the first thing in the vector, and then end of A, which is an iterator pointing just past the 3. So that second iterator is not pointing at data, it's pointing at the first thing past good data. So we never want to dereference that iterator, and the STL, of course, does not do that. In the comments over there, it says that it sorts, excuse me, square brackets left, which that left is inclusive and the parenthesis on the right, which is our half open interval. And you would go up to, but do not include the thing that it's pointed at in the right. So this is a real common way to do it from beginning to end of some container. But if you did want to do some partial area sorted, you could do that with any two iterators. In this lecture, of course, to make things more visual and easy to see, we're going to be using indices and arrays, but we'll still be using them in that same way where we're talking about the index 0 where things start and the index 5, which is where we shouldn't be doing any sorting. So here we've got an array A that's declared and initialized with the same values 4, 2, 5, 1, and 3. So anytime we're starting to work on some things here in the slides, any conversion from one mode to another is always going to be helpful for your understanding. So if it's written in index mode, rewrite it in iterator mode. If it's written in iterator mode, rewrite it in index mode. Make sure that you understand these things. And this is a really good way to do this. First up, we're going to look at how does size affect what I'm sorting. And we've got three general categories of what we consider sorting. We've got internal sorts, indirect sorts, and external sorts. An internal sort is one where it says I can see all the elements. See meaning I can work all of them in memory at the same time. So that's a great way to do it, and I'm able to see and manipulate all of those elements. So when the sequence to be sorted fits in memory and I've got random access to them, I can do these internal sorts. An indirect sort is one where I can see all of the indices. So I may not have all of the data that I can look at, or maybe I don't want to actually change the order of any of the data. But if I look at indices, I can sort the indices. And so here I'm reordering the indices instead of the actual data. Sometimes I can't, like when I've got constant information and I can't reorder them. Or maybe if I've got really large objects and I'd rather have them where they are in memory instead of moving them around with a lot of swaps, I can just put some indices on them and sort those indices. Or sometimes I may have them already in an order that I would like to retain, but I would like an additional ordering, and that's with a different sort. And so indirect sorts allow me to do that. And that's what we looked at when we were looking at the comparators. When we first started talking about functors, we made that sort by coord sort. So if you haven't seen that, go back and look. That's an index sort. So rather than sorting the data, we sorted the indices. So then if you want to look at the data in sorted order, you run through the indices, and each new index in order tells you where to look in the original data. So you can look at those indices in the sorted index container, and they won't generally be in 0, 1, 2, 3, 4, 5 order. But when you get to the 0th location, you take that index and then you go into the data container, and that's where you find the first data item. That's what an indirect sort is. External sorts are when we have too many elements, or maybe we can only access our data sequentially. So here often we'll have items stored on disk, and we'll be sorting them from one disk to another. So our external sorts don't take place in place. So I'll be sorting from one source and possibly another source and writing to a new destination. So that's when I've got too many elements. If I've got too many elements to fit into memory, I might have to sort this in batches. And that's what external sorts are. So for starters, let's write a swap. Just to make sure we understand how we do this, we're going to be swapping when we put things in order while sorting things. So we have two items, A and B. We need to write a sort. So as you think about this, what should your return type be? Is there a return? Can you write a templated version of swap so that we can do like the STL and minimize the amount of code that we actually have to write? Okay, one more hit for external sort. So in external sort, I may have too much data to store in memory. So I can't do the sort. I might have to say, well, bring in this chunk of it, then we'll sort it, and we'll put that chunk over there, and then we're going to bring in the next chunk, and we'll sort that, and we'll put that over there. We'll take the next chunk, we'll sort it and put that, and then I'm going to have to combine those chunks. Or I might have so much data that I can send, a third of it over to this machine, a third of it over to that machine, and a third on this machine right here. They'll all work on sorting part of the data, and then they'll bring it all back together. So that's some of the ways that external sorts get used. We can't have, it's when we can't generally hold all of the information to be sorted in internal memory. So we've got to use external storage to help us along the way while sorting. Okay, our swap exercise here. I'm going to take a drink of water here and give you about 30 seconds to figure out how to write swap. All right, to the answers. Here's swap. It's pretty straightforward. We need a third place to write data to. So this is some temp variable, and here you can see that we've taken and declared temp, written A into temp, set B into A, and then we put temp into B, and that gives us our swap. So this is a simple 3-write swap. It's about the way things have to be done. If you want to get really tricky, you can do some nifty stuff with XORing, but that's always given me a headache. So for the general purpose of swap, we're going to use the 3-item swap. We'll take A and B, write to some temporary location, and swap them out. Down below this, you see this nice templated version here. We've got this type name type, so then we can declare our values as references to type. And we're going to declare a type variable inside there and do our 3-item swap. So this is 2 ways to write swap. However, we don't want to do this. In general, there is a swap in the STL. And swap in the STL, in the very worst case, it's going to do exactly something like this. Or to be clear, it's more like this because it's templated. However, when the STL has some objects that have acceleration, they will use that acceleration. So that's why the swap is there. So at the very worst, standard swap is going to do this. If there's a faster way, it will do it the faster way. What this means is, so if I've got to swap 2 vectors, say I've got a vector of 1,000 items and a vector of 2,000 items. In this version here, without any acceleration, when I make a copy of one, I might have to copy as many as 1,000 items, maybe 2,000 if I'm not very sharp. So I copy 1,000 items, and then I move 2,000 items, and then I put 1,000 items back. That's a lot of writing, and that's what's going to happen in the worst case. But the STL has written the vector, and the vector has acceleration in there. And what the STL vector would do when you call swap on it, it says, oh, if that object has its own swap method, we'll call that. And it turns out vector has its own swap method. And so what a vector would do when swapped with another vector is, rather than copy those 1,000 and 2,000 items multiple times, it's just going to exchange pointers. And so in a constant amount of time, you can swap 2 vectors, which is a really powerful thing to know. Regardless of how much data is in vectors, you can swap 2 of them in a constant amount of time. Because what it will do is just a 3-item swap on the pointers that control the dynamic memory in the vector. And so that's why we would say, don't write your own swap, use standard swap when you can, because standard swap is going to, at the very least, do what you would write here, and at the best, can speed things up tremendously. Let's talk about some desirable qualities here of algorithms. Of course, the asymptotic complexity is one of the primary things that we are concerned about. And when we look at how asymptotic complexity plays out with with sorts, it turns out that it's the number of comparisons and the number of swaps, or sometimes one or the other. But comparisons is A less than B, and then swaps, okay, they're in the wrong order, let's change that. So those are the things that make our sorts take their time. So we'll be looking at the worst case, we'll be looking at average case. Of course, best case is really not that interesting when we're trying to figure things out. We really want to avoid worst case situations and steer ourselves towards average case situations whenever possible. Memory efficiency, of course, is another thing. Once we've talked about our time complexity, we also need to know about memory. Some things we'll be able to sort in place. And when we say sort in place, that means we still need some constant amount of extra memory. And if you're wondering what that constant amount is, it's probably that temp thing that we swapped into. So I've got 1,000 items in this vector. If I can pull one item onto the side and copy things into that and do my swaps, I can sort all 1,000 of these things with some constant amount of extra memory. It says big O of 1 there, and you need one thing to do a temp. But remember that a constant amount just means that it's not going to be linear with the amount of data that is being sorted. So if I need to use 3 of them, but I can sort any number of data items with 3, that's still a constant amount of extra memory. So that's sort in place with a constant amount of extra memory. We've also got sort in place with recursion. You can do sorts with recursion. So there we will be keeping our data in place, but we do have to consider how the stack gets used as we make these recursive calls. Most of the time we can't get recursive sorts to be completely tail recursive, so we will have some stack use there. There's sort in place, but with our indirect sort. So in this case, I'm doing some work in place, or my data doesn't actually move, but I will have a linear amount of additional information. So this is what I like to think of as the sort of the small linear amount. So if I've got 100 megs worth of data that I can turn around and sort with 1K of indices, that's still some linear amount, because if I turned around and said, well, now I've got 200 megs of data, now I would need 2K of indices. So it's linear in the amount of data, but it's not on the same order of magnitude as the data. So it is still linear. So that's this is one of the ways that we see when we're talking about sorting. How do I consider what's going on with memory? And then, of course, we've got these other sorts that need this big omega of n of extra memory, and that means we're going to be using a full copy generally. So I think of that big omega of n as being the lowest I'm going to be is as much data as I have there. So some of those sorts are going to use a full extra copy there, and we'll see some sorts that can't be done in place. We're going to have to make copies of what we're sorting, and then we'll turn around and say, well, here's the sorted version of it. Another one that's pretty interesting is called stability. And so the definition of stability while sorting is that you have to preserve the relative order of items with duplicate keys. Lots of words. What it means is if I've got 2 3s in my data, after I sort them, they should still be in the same relationship to each other. So an early 3 here, a later 3 there, after sorting, like this, next to each other, with the early 3 still coming before the later 3. That's stable. What would not be stable, still a correct sort, but an unstable sort, if I've got my early 3 here, my later 3 there, and then after I sort them, the later 3 now ends up before the early 3. It's still a correct sort, but that's an unstable sort. And why that's important is sometimes when we've got 2-level sorts, so I want to sort first by last name, then by first name. Well, if I don't respect that previous sort, then first I sort by last name, and then as I go to sort things by first name, I scramble all the last name sorts. So if I'm looking to get Abby Smith before Benjamin Smith, if I sort by last name first and it's stable, then the Smith keys stay the same and I come up with A before B. But if it comes around the other way, I might say things turn out differently if in an unstable sort. I might end up with my last name sort being undone because of my first name sort. So that's what's important there. Our elementary sorts tend to be stable. Not all of them are, but most of them are. Our complex sorts are usually not stable. And this stability, as I mentioned, is important for sorting on 2 or more keys. If I wanted to sort alphabetically and then by social security number, or by 2 names, or by department and position, however you wanted to do it. One of my favorite slides of the entire deck here. It's got Charlie Sheen in it. It's hard to beat a slide with Charlie Sheen. So this is more on stability. So it talks about a sorting algorithm being stable if the data with the same key remains in the same relative location. So here's the input data. It's already sorted by first name. We've got Charlie, Sheen, Hallie, Barry, Lucy, Lou, and then Martin, Sheen. So CHLM are my first names. Then if I sort by last name, if I've got a stable sort, the interesting part is when we get to the Sheens, Hallie Berry comes first, then Lucy Lou, because now we're going by last name, B, then L. And then the N has the two Sheens, Charlie and Martin. When it's stable, because they were already in this first name sorted order when I started, because Charlie came before Martin when I started sorting their last names, when it's stable, Charlie remains before Martin. An unstable output might swap those two last names because we were sorting on last name, and that's what this last name sort was about to do. And so I still end up with Barry, Lucy, Sheen, Sheen. But because it was unstable, my first name sort has been broken, and now so I've got Hallie Berry, Lucy Lou, Martin Sheen, Charlie Sheen. So that's what stability is all about. And some sorts are stable and some sorts are not. One of those things that you definitely should write on your exam cheat sheet, because you need to know how to look that stuff up really quickly. Or you could just remember it all. That's really good too. I suggest both. We've got a couple of different ways that we look at our sorting algorithms while they're performing. There's a non-adaptive sort, in which the sequence of operations performed is always the same sequence, no matter what the data is. If it's less sorted or more sorted or completely reversed, it does the same amount of work. Usually it's easier to write these ones because we don't have to do any additional considerations. However, an adaptive sort might look at one really close to sorted piece of data and do less work than one that's not very sorted. So non-adaptive sorts are going to do the same amount of work. Adaptive sorts will find benefits and use them to your advantage. So we'll be looking at making the algorithms that we start with more adaptive whenever possible. And what we'll be comparing is our worst case versus our best case complexity. That's our overview on sorting. We'll get into how we implement a few different sorting algorithms next, and we'll be using the foundation that we laid out here in this overview. Our first sort is bubble sort. There's a couple of different ways to write bubble sort. And just like in the STL, there's some choice that has to be made, with the less as the thing that we use, as an increasing sort being the thing that we care about. So in a bubble sort, you can sort of move small items to the bottom, or you can move big items to the top. At the end of a complete run of that, you will have sorted data either way. So be aware that as you look this up, or you might run across this in other literature or lectures, that you may see it implemented completely opposite of the way that we talk about it today. And that doesn't make us wrong or them wrong. It just makes it the other choice. Okay, so here's bubble sort. It looks really simple, and it is. It's an elementary sort. But let's get right after that complexity first off and foremost. Let's get it done. For starters, I've got two nested for loops. Inside my innermost for loop, I see I've got a comparison and then a swap, which we know how that's all a constant amount of work. So what's inside my innermost for loop is a constant amount of work. So then the complexity of this function is only about how long do these for loops run. Let's take a gander at those for loops. Easily not my favorite for loops. You know how I love a for loop. Start with 0, go up to less than a thing, and plus plus to get there. That's a really nice count control loop, because I can evaluate them very quickly. Other for loops, of course, are very useful, but it takes a little bit more work to figure it out. So look at this first for loop in line 2. It says size t of I is equal to left. I is less than right minus 1 plus plus I. So it looks like it's going to be a linear for loop because it's got an increment in it, a plus plus, so we're going by ones. Then if I look at the size of it, I say that it can start at the left and go up to, but not quite include the right. So there's, if it was from left to I minus right, it would be the whole thing. But it's I less than, instead of going from left to I less than right, it's going from left to I less than right minus 1. So it looks like we're shaving an additional 1 off the end. As I pass the data in there in line 1, I've got my data in some array A, and then I've got left and right where the sort begins and just past where the sort ends. Excuse me. So that first loop, if I had to do some analysis on it, it doesn't look like it goes through all n of the items. It looks like that outer loop goes n minus 1 times. Still means it's a big O of n loop, but it's an n minus 1 times kind of loop, and we'll look at why that is later. The inner loop, what have I got going on there? Now this is a minus minus loop. That's for j equals right minus 1 as long as j is greater than I minus minus j. These are a little bit harder to track once we start making our loops rely on each other. So when I say that j goes from right minus 1, that's almost to the end again, right? Now since right is just past the good data, I will say that right minus 1 is actually pointing at the last item in the range. That's where we start. And then we go for j greater than I. So this is going to change as my outer loop runs, but the way that you think about working on your complexities, you look at the worst case. So what is the farthest that I can be from right minus 1? And it's of course at the very beginning when I is initialized to left. So my inner loop goes from right minus 1 to left. My outer loop goes from left to right minus 1. So it looks like I've got a couple of n-based loops, even though one's going plus plus and the other is going minus minus. So bubble sort is then analyzed to be an n squared time algorithm. That's how I pull that off. What it does is it finds the smallest item in the first pass by looking at these things two at a time. Starts at the right side, and then it says if these two are out of order, swap them. Then move one to the left. If those two are out of order, swap them. If they're not, move on. Move one to the left. Every time I find a pair that are out of order, I swap them. And what this has the effect of doing is during that first pass, the smallest item works its way all the way to the left. So if you think about bubbles in water, that smallest item goes all the way to the bottom of the tank. And my bigger items are sort of floating upwards, which is where the name bubble sort comes from. So after my first pass, the smallest item is in the first position. After the second pass, the second smallest item is in the second position. Then the third pass, third item, third smallest position, and so on. We keep going this way, and this tells us why my outer loop there in line 2 has n minus 1 iterations, right? Because if I take and put the n minus 1 smallest items in their perfect position, all that's left is the largest item, and it has to be in the last position. So we don't have to sort that last item. So this is a little bit of speed up there by saying I only have to sort n minus 1 items if I put them all where they absolutely belong, because the last unsorted item has to be where it belongs, because all of the other items are already set to their ultimate positions. We will repeat until this is sorted. Obviously, that's what the loops are doing. And this is the non-adaptive version, right? It's going to go through this inner loop and the outer loop the same number of times no matter what. If I've got completely sorted data and I pass this to bubble sort, it's still going to run n squared time to say, yes, this data is completely sorted and we have done nothing to it. Our example here starts with that same data we've already looked at 4, 2, 5, 1, and 3. Since we're going to start from the right side, we're going to look at that pair on the far side. I've got 1 and 3. Are they in the right order? Yes, they are. 1 comes before 3. That's great. As I move in, the next pair that I look at is 5 and 1. They are not in the right order. 5 comes before 1, so I do a swap. That'll give me 4, 2, 1, 5, 3. Then I compare the 2 and the 1, and those things need to be swapped. They're in the wrong order, so I'll end up with 4, 1, 2, 5, 3. And lastly, I'll check the farthest left pair, which is the 4 and 1, and see that I need to update that so that 1 and 4 get swapped. So after that first pass, I've made 3 swaps. And I end up with data that looks like 1, 4, 2, 5, 3. So my bigger item, the 5, is kind of moving its way to the right. It's bubbling up to the top, if you will. And my smallest item, that 1, has sunk to the bottom, or it's moved to the very first position where the smallest item should be. The second pass starts at the far right again. It compares 5 and 3. We see that they're out of order, so I'll do a swap there that puts the 3 to the left of 5. Then I move 1 to the left and compare 2 and 3, which are in the right order, so no swap occurs. And then I'll check the last pair on this path, which is 2 and 4, and I will have to swap them there. So that's why we go down to I in the inner loop, because once I've put that 1 in the first position, I don't need to do any comparisons to swap it. So I'll have to do 4 comparisons in the first pass, 3 comparisons in the second pass, 2 comparisons in the third pass, and so on until I'm not having to compare any items. So after the second pass, we see that the second smallest item is in the second position. Larger items continue to bubble up. The 5th item is actually bubbled all the way to the top, and that's just an extra benefit. We haven't made that happen yet, and in reality, the sorting algorithm doesn't understand that the largest item is in place, even though it happens to be. All the algorithm knows is that 2 passes in, 2 items are exactly where they belong, the first 2. So we need another pass. This next pass is going to check out the 3 and 5, see that they're already in the right order, leave them alone. Then check the 3 and 4, see that they're in the wrong order, and swap them. And that's where the third pass stops. Now the data looks like 1, 2, 3, 4, 5. It is completely sorted, but after having 3 passes, the algorithm only knows that the first 3 items are sorted. The fact that the last 2 are sorted is incidental. It's accidental. It's just the way that it happens. So the algorithm has to do one more pass to check to see that those last 2 items get put in their proper order. So that 4th pass does nothing. But it tells the algorithm that the first 4 items are exactly where they belong, and thus the 5th item must be where it belongs as well. So after these n-1 passes, bubble sort has done all of our work. It's got us sorted here in place. So we've done this with a constant amount of additional memory. All we needed was 1 additional place to swap things with, and it's done it in this n² time, because I've done these n-1 passes dealing with as many as n items per pass. So that's n², big O n². So it's not adaptive. We talked about that. We talked about in that last one where we didn't have any work to do, it still had to do some work. How can we write bubble sort in a way that makes it adaptive? So if I don't have to do any more work, I want to stop early. That's what an adaptive sort will do for me. The hint given says, think about what happens if we try to bubble sort something that's already sorted, 1, 2, 3, 4, 5. How do we do that? How do we make this algorithm a little smarter? Remember, sorts are about comparisons and swaps. Okay, hopefully you've pulled that off. When no swaps are done, perfect, Surya, that's perfect, right? Because it's about comparisons and swaps, if I make it through an entire pass of comparisons and have done no swaps, any further passes are just going to do comparison, comparison, comparison without swaps. So that's how we can make this adaptive. We've kind of broken out our swap now, and swap has changed into the actual 3 lines that we see here, 5, 6, and 7. So what was earlier going on in our comparison and swap was in 5 and 7. Now we're saying if a swap is made, we're going to set some Boolean, which we call swapped, equal to true. And every time we use that Boolean, we're going to initialize that at the beginning of an inner loop. The outer loop does all of the items. The inner loop says I'm going to do this pass. And so if I say I haven't done any swaps and then start an inner loop, anytime I do a swap, I mark a swap as true. So noting that I have swapped something. Then at the very end here, lines 10 and 11, I see if I've made it through an entire inner pass without swapping, I can stop. So if I haven't swapped anything by line 10, that means there's no more swapping to be done. That means the data is sorted. Without a swap there, I can break, and that break gets me out of my outer loop, which gets me out of the function. So this is an adaptive bubble sort. It's not extremely adaptive. It does save us some time, though, when we're getting near the end. When we've got data that's already sorted, we can get this done in one full pass of comparisons and say, hey, this is already sorted. I did no swaps. We're done. As we get something closer to swapped, closer to sorted, if I run into a situation where the last 10 items are sorted, I'll make one pass before that and then decide there's no more work to be done. So it does help us out a little bit. In our non-adaptive version, we say that it's approximately n squared over 2 comparisons and swaps in my worst and average case. I can say that there's n squared over 2 comparisons and 0 swaps in the best case, because I still do all of the for loop stuff. I just do no swaps when the data is already sorted. So in my worst and average and even my best case, we see that the non-adaptive version of bubble sort does n squared work. And that approximately n squared over 2 comparisons looks like n times n minus 1 over 2. So that's just like the handshake problem. How many handshakes do we have to do if we're going to introduce a whole room full of strangers? It's going to be n squared, a big O of n squared. In my adaptive versions, nothing really changes in the worst and average case, right? I still am doing those n squared over 2 comparisons and swaps. However, in the best case, now we know that we can do one full pass on the sorted data, comparing everything, finding nothing to be swapped, and be done. So it turns out with my adaptive version, in the best case, I've got now a linear sort, which is really like a linear leave it alone kind of thing. So don't think of any sort as being really that linear. There's a linear leave it alone. I end up with approximately n swaps here now, so things have gotten better. I can get to as few as 0 swaps, obviously, in the best case. So this is a great reduction for our best case sorting, which is great, but usually we're most concerned about what's going to happen in the worst case. So our adaptive version does make some improvements, but we can see that in the average case and in the worst case, it's no better. So we can't get any better, as I mentioned earlier when we were talking about tuning and making some improvements to these things. We're never going to really jump a complexity class. Bubble sort's advantages, of course, it's simple, easy to implement and understand. Our first version of it was written in 4 lines of code plus a function header. It does do some pre-sorting, as we saw the big numbers floating up to the top. So even when I was partially done, I was more likely to incur to run into larger items on the big side as my small side got sorted. It's also stable, which is great. As we look at 2 3s, I have no reason to swap them because the first 3 is not smaller than the second 3, so they just get skipped. So things that are previously sorted stay previously sorted. The adaptive version can finish quickly if the input array is almost sorted, so that's an advantage there. The disadvantages, of course, is this is big O n squared. It's big O n squared, it's big O n squared. It's an elementary sort, it's big O n squared. Not going to get ready, not going to get away from that. That means it's slower than our high performance sorts. We've got this n squared over 2 comparisons and n squared over 2 swaps, approximately. That's bubble sort, and we're going to move on next to our next sort, which is selection sort. This is an elementary sort as well. This one mimics a process that we do more often when we're dealing with things. You've got a bunch of things to sort. Usually you got a mixed up deck of cards. You'll sort of find the ace, 2, 3, 4, 5. You'll find that smallest item, then find the second smallest item, then find the third smallest item. That's how selection sort works. So it's going to be hard to sort of distinguish these two. I remember I had with these 3, I had a real tough time in the beginning, years sorting out my sorts, if you will. Knowing the difference between bubble sort, selection sort, and insertion sort, they all make great sense. It's hard to figure out what separates them in your mind. So in selection sort, what happens is we're still going to put the smallest item into the first position first, and then the second smallest item into the second position, and then the third smallest item into the third position, just like in bubble sort. However, instead of swapping these things pairwise, what we're going to do is first kind of do a linear search to find the smallest item, and then swap it with one swap into position. Then we'll do a linear search on what remains to find the second smallest item, and swap it with one swap into the second position. So here's how the code looks. We've got a couple of for loops there in lines 2 and 4. Inside the inner for loop, I see I've got something similar there with a constant amount of work. I've got a comparison and an assignment. Line 7 has another assignment. That's inside the outer loop, but it's a constant amount of work here. I've got some constant amount of work in line 3. So in the end, the only thing that looks really interesting in terms of complexity are the two for loops, lines 2 and 4. Both of them are plus for loops. They're probably going to be linear. I just have to figure out how wide they are. The outer loop goes from left to I, right, -1 again. So it looks like that n-1 outer loop that we saw previously. And then the inner loop goes from j at I +1 all the way up to right. So I have to compare I's worst case in the outer loop, and that'd be right -1. If I add 1 to that, or sorry, that's left. So left +1 is as far away from right as my inner loop can be. So it looks like I've got myself a couple of n-ish loops here, n-1 loops. So I'll say that that outer loop is n-1, big O of n, inner loop, big O of n as well. So this whole thing is big O n squared. So the selection sort, like our other elementary sorts, n squared. Not surprising, it's not great in terms of complexity. But it works slightly differently. It finds the smallest item, swaps it into place, repeat, repeat, repeat. It is non-adaptive as well. So here is how it works. We're going to take that same data we've used, 4, 2, 5, 1, 3, and in the selection sort, I'm just going to do a linear search, 4, 2, 5, 1, 3, find the smallest item. First it's 4, then I find 2, that's better, 2 is my smallest item, 5, no improvement, then I find 1, that's my smallest item, and 3, no improvement. Once I've done that, I hit line 7 because my inner loop goes through all of the things that I'm investigating, and once I fall out of the inner loop, I know where the smallest item is. I set that minimum index here in line 6. So after that first pass, it says my minimum index would be index 3 there, and then I'm going to do a swap from index 0 to index 3. So it puts the 4 in the first, the 1 in the first position and the 4 there in that fourth position, that index 3. So now after pass 1, I've got 1, 2, 5, 4, 3. My data is getting sorted because I have the first position is absolutely correct. In my next pass, we'll see that the second item is already where it belongs. However, the algorithm has no idea. So it's going to do an inner loop to look at 2 and see that's the best. Then it's going to look at 5, see that's no improvement. Look at 4, no improvement. Look at 3, no improvement. Inner loop complete. Minimum index there, 1. And then in line 7, I do this crazy thing where I swap 2 with 2. That's the way it works. I'm trying to swap that second smallest item into the second position, and the second smallest item is already in the second position. So the swap happens anyways. We do a swap from 2 to 2. After the second pass, the algorithm knows that 1 and 2 are completely sorted, and the remaining 3 items still need work. So my third pass, right, I'm going to go through the remaining 3 items, 5, 4, and 3, find the smallest one, that's 3, swap it into the third position with the 5. And after 3 passes, the algorithm knows 1, 2, and 3 are completely sorted and knows nothing about 4 and 5, which are, incidentally, already sorted as well. But the algorithm doesn't know that. It has to do one more pass to find the smallest remaining item out of 4 and 5. Once it finds that, 4, it swaps it to where it belongs, which is where it is already. So we've got another call here in line 7 to swap some item with itself. In this case, I is equal to 3, and min index is also equal to 3. So we swap 4 with 4, and then the algorithm is convinced that the entire thing is done here. All right, so that's what it looks like after sorting 1, 2, 3, 4, 5. Nothing exciting there. But we do see that we do some unnecessary work, just like when we were looking at the bubble sort and we saw, well, if we're going to do a whole pass with no swaps, I don't have any more work to do here. Here we did some unnecessary work, you might think. Swapping an item with itself is unnecessary. And that's about all the work that we can do to make this a bit more adaptive. We can say if the min index is not equal to I in line 7, instead of swapping in line 7, we check to see if there's a swap to be done. And if there's no swap to be done, we don't do it. But if there is a swap to be done, we do the swap. So not a lot of improvement there because we actually added extra work to make sure that I need to swap something, because most of the time I do swap. Even in that small example, most of the time I'm doing swaps. So here I'm doing this check to say, hey, should I really do a swap? And most of the time the answer is yes. You still end up doing the swap. So you end up with a little bit more work there. And the only time this is beneficial is when my swaps are very expensive. So if I've got really large data and it costs me a lot of time to move data, say more time than it takes to do a comparison, I would rather do the comparison and save me swapping the data. So adaptive selection sort is not a huge improvement. It's a minuscule improvement, if it's an improvement at all. In the worst case, it's not an improvement at all because I'm just adding a bunch of extra comparisons and still doing the same amount of swaps. So this is only great when I've got really large data and I know that, just saving one unnecessary swap could be, a huge speed boost. So that's what adaptive selection sort looks like. It hasn't done much at all. As we do our analysis here, I mentioned this was already an n-squared sort. It does approximately n-squared over 2 comparisons. We're still, at the end of the day, our elementary sorts look at every pair of items. How do you two get along? I'll do some swapping or whatever. So that n-squared over 2, that big O of n-squared, is because every pair of items is being compared. In the non-adaptive version, we always do that n-squared over 2 comparisons. Then we do the n-1 swaps because every pass on the inner, we put something into place. So that's n-1 swaps in the best, average, and worst case when we were non-adaptive, because even when we needed to swap something with itself to get that n-1 swaps in, we did it, even if it didn't make sense. Our runtime was insensitive to input because we always did a swap every pass no matter what. In our adaptive version, we still do the same number of comparisons that we were doing before, this n-squared over 2 approximate run. We see here it's more exact here. It's n-squared minus n over 2. That's the approximately n-squared over 2 comparisons. And we've also added an additional check to see, should I do this swap because I've got 2 unique items. So I've added an additional n-1 comparisons. So the big O of comparisons has not changed, but I am doing more. It's still big O of n-squared. But I'm doing more swaps. Now I'm still, in the worst case, going to be doing the same number of swaps. Sorry, I said I'm still doing the same number of comparisons plus an additional round of comparisons. Down here, I'm still doing the same number of swaps in the worst case. As I mentioned, this adaptive version doesn't get better on worst case data. It gets worse. But in the best case, or maybe even in some average case, I might save myself some work here because I don't have to do any unnecessary swaps. So we say that now the runtime is sensitive to input. It's not very sensitive. It is only slightly sensitive to input. But we've added some sensitivity there and we get a little bit of speed. The selection sort has its advantages. There's the minimal copying of items. We don't write data as much. When we were doing bubble sort, it was this constant temp AB, temp AB, temp AB while we were swapping things. Whereas in selection sort, we do the entire linear search and do one temp AB, and we're done with an entire pass. So this is a good choice when my objects are large and copying is expensive. It's fairly efficient for small n, but it's still not our favorite sort here. The disadvantages are all the elementary sort disadvantages, which is it's an n-squared algorithm. And in this case, we're going to say it's tightly bound. It's going to be almost always n-squared. So best case, worst case, average case, n-squared here, right? Because we've got to do those comparisons. no matter what, the comparisons are going to sync us to n squared all the time. Even in our most adaptive version, it's n squared. The runtime is only slightly dependent upon the pre-ordering, so it gets a little better, but not much. So this is noted by the fact that the smallest key that we put into place on the first pass doesn't tell us anything about the other things that we found in that pass. So we don't know where the second smallest one is. We could move the second smallest one all the way to the end just to put the first smallest one in the front if the second smallest one was there. So it's now gone a lot farther away than it needed to be. But that's the way that the sort works. It ends up running about the same on an already sorted array, and the thing where all the keys are equal, or a randomly arranged array, it's always the same and always slow. That's what selection sort is. And it's also not even stable. So if we've got some other sort that we're pairing it with, we've lost information. So selection sort is more disadvantages than it is advantages. Its primary advantage is it moves data less. So if you've got a lot of data to move, as in large items, not just a lot of things to be sorted, large items, then selection sort may be your friend. There's things that are always going to give you a reason to depend here. Here's my simple summary on these things. I'm going to say that the sorting algorithms are useful to satisfy these direct requests to sort something and do it quickly. The ones that we looked at, bubble and selection sort, are what we call slow sorts. They're asymptotically slow. It's n squared. That's a slow sort. We know that our best theoretical sort is going to be n log n, so anything slower than that's a slow sort. So n squared is what we've got going on here, and that's what I'm talking about, comparison sorts. We've got a minimal opportunity for tuning. Next up, we're going to look at insertion sort. It's also an elementary sort. It's also asymptotically slow. It's also big O n squared. But we will tune it a little more, and we'll see some nice little tricks here as we move into insertion sort. Here's insertion sort. If you think back to what our first version of bubble sort looked like, this looks almost identical, which is why I mentioned having a problem distinguishing insertion sort, bubble sort, selection sort when you're first learning these sorts. So this one's got a couple of for loops, and then inside the innermost for loops, I've got an if comparison and a swap. It looks exactly the same. The only difference here is the range of my for loops and where they work. So the incoming data is still A. We've got a left and right where the sort begins and just after where the sort ends. I've got an outer for loop that's a plus plus, and I've got an inner for loop that's a minus minus with a constant amount of work inside there. It's only the size of my for loops that make the difference. The outer loop goes from left plus 1 all the way up to, but not including right. So that looks like an n minus 1 outer loop. Now we've skipped one again. And the reason why we skip one is the same reason that we skipped one previously. If I can do this sort, I don't have to sort all the items. I just have to sort all but one of them. And if all the rest of them are where they belong, things are going to be good. My inner loop starts out at I and goes all the way, as long as it's greater than left, it stays up there, and then it minuses. So I have to look at what my worst case could be. I could be all the way up to right minus 1 and then go down to left, so that looks to be an n-based loop again as well. So this is why we get the n squared here. All right, the way that insertion sort works, however, is that it starts with your data and divides it into two categories, that which is sorted and that which is not sorted. And one by one, it takes something from the unsorted section and inserts it where it belongs in the sorted section. So where it starts is say, well, any one item is already sorted. So if I divide this size n container into two parts, I can say, well, the first item is sorted. It's just these n minus 1 other things that I need to fix. So that's what my n minus 1 passes are. It takes one of those items from the rest of them and puts them where they belong. So the first item is already sorted by itself, no matter what it is. It could be the biggest item, it could be the smallest item, or anywhere in between. But if I consider that item all by itself, it is already sorted. Then it goes into the area of unsorted and takes one item and decides, do I move this in front of this item, or do I keep it where it is? If there's 3 items, I've got to figure out somewhere in those 3 items to place this 4th item. If there's 4 items, I got to find somewhere in these 4 items to place this 5th item. And that's what insertion sort does. It moves items one at a time from the unsorted list to the sorted list. and inserts it into its proper place. So I'll have some sublist that's already sorted, the first sort of k items. And then I'll have the remaining n minus k items that are unsorted that need to be inserted somewhere in that k to be sorted. So it doesn't matter which k items they are, they can be sorted amongst themselves without concern for the overall list. And then we'll insert, as we insert the remaining n minus k things in there, they will eventually end up in their ultimate position. This sort, as you might imagine, is non-adaptive. There's one comparison in the entire thing, right? If a sub j is less than a sub j minus 1, that's the only comparison that we write other than our for loops. So not adaptive. In our insertion sort example, we'll start here with our same data, 4, 2, 5, 1, 3. As we start to do our insertions, we note that 4 is already sorted. All I have to figure out is where to put 2, 5, 1, and 3 with relation to 4. So my first pass says 4 is good. What do we do with 2? Do we leave 2 behind 4, or do we move 2 in front of 4? And of course, it should be moved in front of 4, and that's what the first pass has done here. After pass 1, I've got data 2, 4, 5, 1, and 3. One pass in, insertion sort thinks 2 things are sorted, because without even doing a pass, we already knew 1 thing was sorted. So here, after 1 pass, I've got 2 things sorted, 2, 5. Even though 2, 4, even though 5 is where it belongs, the algorithm doesn't know or care. Second pass, we're trying to figure out where to put 5 in relation to 2 and 4. Says, does it belong after 4? Does it belong between 4 and 2? Does it belong before 2? Well, no, it belongs where it is, so we're going to leave it right there. Next pass. Right? So nothing has changed after pass 2. We still have 2, 4, 5, 1, and 3, but now the algorithm thinks 2, 4, and 5 are all sorted, and it only has to work on 1 and 3. The next insertion that needs to be done is, where does 1 belong? Does it stay after the 5? Does it go between the 4 and the 5? Does it go between the 2 and the 4? Or should it be put in front of the 2? Each time this kind of feels bubblish. So we'll look at that 1 and say it belongs before the 5, so we do a swap there. The 1 belongs before the 4, so we do a swap there. The 1 belongs before the 2, we do a swap there. That's how pass 3 shakes out, and that's why we've got 4 items sorted. 1, 2, 4, 5, and then 3. Our last pass just needs to put the last item into place. It's the 3. It should either stay where it is, it should go before the 5, it should go before the 4, it should go before the 2, or it should go before the 1. And that's what this inner for loop with the if check does. It says, should I move it forward? And it turns out that I should. I end up moving that one in there. And the reason why we say this is non-adaptive, because this inner loop continues all the way to the left as it does that inner swapping. So in the previous version, we had 1, 2, 4, and 5, followed by 3. So the 3 and the 5 get swapped, and then we've got 1, 2, 4, 3, 5. Then the 3 and the 4 get swapped. We've got 1, 2, 3, 4, 5. And then the inner loop checks the 2 and the 3 to see if they need to be swapped, but they don't. So then it checks the 1 and the 2 to see if they need to be swapped, but they don't. And that's what a full pass is. So that inner pass on line 3, that for loop in line 3, goes all the way to the left-hand side every time. That's why I said J is greater than left. That's the test in my for loop in line 3. So there is, if you're looking, some great options for some adaptive work there. Once I've got that 3 as far as it's going, there's no need to check the previously sorted items for additional swapping. But this is the simplest way we could write that, and we'll add some more into it. So we've got the concept of insertion across. Now we'll see if we can't tune it up a bit. First, let's analyze it as is. In my non-adaptive version, I've got this n squared over 2 comparisons. There's no surprise there. That's in the worst case. In the best case, every time I find something out of place, I gotta, In the worst case, I've got n squared over 2 comparisons. In terms of swaps, in that same worst case, I'm still going to be swapping everything. So every time I compare, I see that they're out of order, I do another swap. So I've got n squared over 2 swaps in the worst case. So worst case, this is obviously an n squared algorithm. In the average case, I say about half the time I need to make those swaps when I do a comparison, which sounds like an improvement. It's not. Asymptotically, it's not an improvement, because now I say in the average case I'm going to do n squared over 4 swaps, which is still a big O of n squared in the swapping area. So I say that our runtime is only slightly sensitive to input. The comparisons are always the same, but the swaps can be slightly reduced. So that's what it looks like when it's non-adaptive. We're going to improve this, however, by taking this and trying to figure out how can I minimize comparisons or swaps or both. Obviously, the best way to get a better sort is to use a better algorithm, but since we're stuck with insertion sort, we're going to tune this one up, and the best way to do that is to go as deep as you can in the algorithm. If there's nested loops, your primary improvement is coming from changing things as deeply as you can, because that's the stuff that gets done the most. So if we can tighten the inner loop in terms of comparisons and swaps, that's where we're going to get some adaptive improvement here. So here's our first improvement. We've been talking swap, 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 swap. That's the temp equals A equals B equals temp. We've done that. There's 3 writes involved there. We have to write from A to temp, we write from B to A, and then we write from temp to B. So there's 3 write operations where we write from some place in our processor to some other place in our processor. So this version uses something called a move instead of a swap. It's pretty straightforward. If I've got, for instance, one item that needs to be swapped 10 positions, instead of having swap 1, swap 2, swap 3, swap 4, swap 5, instead of doing these 9 swaps to move this thing over 10 positions, I can do a move. And what the move does is it says, instead of putting this thing one at a time, I'm going to take the item that's going to be put into position, write it off to a temporary location. So there's my first write. Then I'm going to move things over one at a time where they belong. And then when I'm done, I can write the thing that was to be put in place where it belongs. So what this does is it reduces the number of writes that I have to do. So with that move, I've got the 1 out, and then I can move the 9 over, and I can move the 1 back in. So that turns me into some linear number of writes. It was already a linear number of writes. It was 3 writes per swap, so I was already doing 3K writes. Now I can end up doing my temporary write and my shift over and an additional write at the end there. So now I've gone and reduced my total number of writes by a factor of 3, which is an improvement. This gets done by sort of deconstructing what I had going on there. I had an inner for loop, and now I'm going to pull out that size T initialization of J outside of the for loop, because I need to keep J after I get done. What I'm going to be doing is use that J to where I'm going to be write the data at. So here in line 12, I got A square brackets J equals to V. And so if J was declared here in the for loop, outside of the for loop, it would be out of scope. So the J has been pulled out to be declared before the for loop. That's the first change. The second change is we're going to take this, if A at J is less than J minus 1, do the swap. Here we're not going to do the swap. We're just going to turn this into a, if V is less than what's at A at J minus 1, then move the thing over by 1. Set A at J equal to A at J minus 1. That's moving something from the left 1 space to the right. What's V? V is, of course, the value that we're trying to put in position. That gets assigned here in line 3. So inside my outer loop, I say the value that I'm now trying to insert is V. I do the work here and move the things out of the way in the rest of the inner for loop, and then at the very end, I put the item that was to be put in position where it belongs with a single write. So that's an improvement now. We've reduced the total number of writes. This next slide is a setup for my second improvement. So nothing has changed in this slide to the last slide other than the way that it was written. So these two are exactly the same in execution, but instead of using a for loop, we've used a while loop and included the increment step inside of the while loop. So these two pieces of code compiled probably identical, but it looks a little bit different when we write it. So that's what's great about it, because it's going to set up what I want to do next. So we've replaced the for loop with a while, and we've removed the break. So inside there, we were using a break statement. If v was less than a at j minus 1, we were going to do some work. But now we've taken that check from inside the while loop, from inside the for loop to being in the condition of the while loop. So the break happens at the conditional check. Instead of having to go inside and break out, we just fail and don't go into the while. So that's all that's happened here. We've just kind of refactored the existing slide. No improvements, but it does set up my improvement now. This is what it looks like when I'm completely refactored with a while loop. Right? The while, which is now my inner loop, says while j is greater than left and the value v is less than what's in a at j minus 1. I'm going to slide something over. That's what happens in line 5, and then we jog down 1 in line 6 with our decrement there. So while I haven't hit the far left and the value that I'm looking at is out of place, move something over. That's what the while loop says. While I haven't hit the far left and the value that I'm looking at is out of place, move something over. So we see here that this j is greater than left test happens all the time. It's the first thing that we do in our while loop. Think about what that means though. While I haven't hit the far left, while I haven't hit the beginning of my container. Now imagine you're sorting something with 5,000 items and you're about halfway through the sort. So you've inserted 2,500 things and you're trying to figure out, where should I insert this 2,501st item? You say, well, have I hit the beginning? No, you're at 2,500. You run through the loop, you say, well, have I hit the beginning? No, you're at 2,499. You run through, have I hit the beginning? No, you're at 2,498. No, you're at 2,497. So that while have I hit the left side happens a lot. And most of the time it's false. I haven't hit the beginning because I've got so many things I'm sorting and I know that there's a lot of them. We need that though, because I don't want to take that j at left and then subtract 1 from it and try to dereference a, because then I will be looking at something out of bounds. So I need that check there. It keeps me safe. It keeps me from looking past the beginning of my data. So that's why it's there. But if we use what's known as a sentinel, then I can avoid that altogether. And what a sentinel is it's going to be a data item that my data check never lets me pass. So right now I've got a positional check, that's the j greater than left, and I combine that with a data check while v is less than a at j minus 1. So I've combined those two to keep me in the loop. What I do with the sentinel is I say I can eliminate that positional check by putting the very smallest item first. Because if the very smallest item is first, that second data check will always fail before it falls off the front of my data. Does that make sense? If v is less than a at j minus 1, then stop. Well, if I know that the smallest item is at j minus 1, if I know that the smallest item is at the beginning, v will never, whatever I'm trying to insert will never be smaller than that. And so I'll never try to check anything before the first item. So that's what happens in this next version. We see what looks like an inner pass of bubble sort in lines 2, 3, and 4. And that's exactly what it is, because remember that the bubble sort would take that first inner pass. Every inner pass put the smallest remaining item as far left as it could. So I run this 2, 3, 4, which in a linear amount of time puts the smallest item at the beginning of my container. Now in line 8, where my while loop is, I can eliminate that positional check because I know that the data check is never going to fail and allow me to come off the front, because no value that I will ever be able to insert after lines 2, 3, and 4 will ever be smaller than the first item. So the rest of this is insertion sort just as it was before. This is an inner loop of bubble sort. Why do we use the inner loop of bubble sort? Because it's stable. So if I use this stable version, then I've got a stable insertion sort. So that's great. I could say do a little bit less work by putting a selection sort here, which would be great, except it wouldn't necessarily be stable anymore. So I've used bubble sort here because it's simple, it's because it's stable, and it's because it sets up my sentinel in a way that I can eliminate this check here. And what have I done? I've eliminated a comparison from inside my inner loop. And that's tuning right there. That was gonna happen n squared times. I can take out a factor of n squared here. Like, so now I have 5n squared, it looks like 4n squared, or 7n squared has gone down to 6n squared. That's an improvement. So this is our last tuning of insertion sort. And we've made something now that's a bit faster. It's the best insertion sort we can write. With this adaptive version, we're going to try our initial data 4, 2, 5, 1, 3. After my first pass, the bubble sort pass, it swaps the 1 and 5, the 1 and 2, the 1 and 4, and now I end up with the data that looks like A equals 1, 4, 2, 5, 3. It knows the 1 is where it belongs, and then it's going to do an insertion sort on 4, 2, 5, 1, 3. Noting that 1, 4 is already sorted. 2, 5, and 3 are the only things that need to be inserted, which is why my outer loop here in line 6 now starts at left plus 2, because the sentinel is good, and then anything that follows the sentinel is sorted as well. So now I just have to insertion sort 2, 5, and 3, noting that whenever I fail to be able to move something to the left, I'm good, I can stop. So I try to insert the 2, it does belong before the 4, but fails to get in front of the 1, and after pass 1 of the inserting, I end up with 1, 2, and 4. Now 5 has to figure out where it belongs. It does not go before the 4, so pass 2 happens, and I end up with 1, 2, 4, 5, 3 again. But now the sorting algorithm thinks those first 4 items are sorted. 1, 2, 4, and 5 are sorted. Now, as I go to insert the 3, I just have to say, well, is it less than 5? Yes, we'll move that there eventually. Is it less than 4? Yes, we'll move that there eventually as well. Is it less than 2? No, it's not less than 2. So let's put it right after the 2, and then we're done. We end up with 1, 2, 3, 4, and 5. That's our insertion sort. As we look at it from the analysis side, we see that we still have our worst case, average case, n squared comparisons. N squared over 2 in the worst case, n squared over 4 in the average case. But in the best case, insertion has now gone down to approximately n comparisons. That's an improvement. That's good. So we've got already sorted data. Insertion sort has just lost a lot of penalty. When I'm talking about copies, right, this is the number of data writes that I'm doing. It was n squared over 2 in the worst case, n squared over 2 in the average case, and now it's n in the best case. But we know that we're doing fewer of them because we're not doing 3 times as many for the swaps than we need to do for the moves. Runtime is now sensitive to input, and it makes insertion sort as fast as it can be. The advantages, of course, we're using more efficient data manipulation. We're using move instead, so that's a third of the work of a swap. We're doing fewer comparisons and copies because we're not doing a position check and a data check. We're only doing a data check. We're using only when the key is smaller than the key of the item being inserted. We do find that sentinel key, that's our greatest improvement there. That adds some overhead to the explicit first pass, but it does speeds things up throughout the rest of the algorithm. So remember, we like to think about our ends as being very large. So one linear pass when I'm sorting 100,000 items is not painful if it cuts off a whole bunch of other comparisons for me. So that's great. The advantages of insertion sort, of course, are as runtime depends upon the initial order of the keys in the input. If the stuff is already almost sorted, insertion sort is great. It does very little work for data that's already almost sorted. That's why it's a really good sort when it's small. One of the reasons why it's a good sort when it's small. It's stable, of course, and it's tunable. We looked at tuning it, and you can see that since you never swap anything below its an equal value of itself, it will be stable. The disadvantages, of course, is it's still n squared, and that's a theta there. It means best case, worst case, right? It's not best case, worst case, but our tightest there is an n squared. That's insertion sort. As we look at sorting performance, we've got some comparisons here, some characteristics that we talked about earlier. Runtime is going to be proportional to the number of comparisons, proportional to the number of swaps. Sometimes it's both. All of my elementary sorts were quadratic. And so how do we analyze this thing? One way to look at this is, I talked about things that are partially sorted or mostly sorted or very unsorted, and we need a definition that gets us there. We're going to do that with something called an inversion. And that's me looking at any pair of keys that are out of order. So when I had 5 followed by 1, that's a pair of keys that are out of order, because if things were sorted, the 1 would come before the 5. So I can take every item in a data set and look at how many inversions that it generates. So an early 5 generates a lot of inversions. It should end up after all of those other things. So if you go through every input, count the total number of inversions, you can get some sense of pre-sortedness. How sorted is the data already? Or you can say, well, after a couple of passes, how sorted is the data now? So it gives you a metric to see whether or not data is sorted or how sorted it is. So it's pretty easy to see that the maximum number of inversions would be something that would be reverse sorted, and the minimum number of inversions, 0, would be something that is already completely sorted. So as we've got these inversions defined now, I can say that insertion sort and bubble sort use a linear number of comparisons and swaps. Hey, that's good. I hear something linear to do with sorting. That's good. A linear number of comparisons and swaps for data that has a constant upper limit to the number of inversions for each element. Oh, a constant upper limit to the number of inversions for each element. So that means that it's already sorted. Each element is not very far out of place. Each element may be small number of inversions away from where it belongs, but we don't have any elements that are almost n away from where they belong. So when that's the case, insertion sort and bubble sort are very efficient on partially sorted data, as long as each item is close to its final position. So that's good. Next property. Insertion sort uses a linear number of comparisons and swaps for data with a constant number of elements having more than a constant number of inversions. So if there's a small number of elements that are way out of place, insertion sort still does a linear number of comparisons and swaps. That's great. So the interpretation is insertion sort is efficient on sorted data when a new item is added to the sorted data, which is why we did an insertion sort when we wrote the sorted priority queue. You figured out where the thing needed to be and then you inserted it there. I think this is the last one here. The property that selection sort runs in linear time for data with large items and small keys, right? When selection sort being expensive in comparisons is cheap in terms of swaps, that's great, because that linear number of swaps, if that's what's driving my total time, makes this look like a linear algorithm, because really fast comparisons, even though there's n squared of them, may take a lot less time than that linear number of moves, which was going to happen no matter what. So selection sort can be linear sometimes. Here's our summary. We looked at some n squared time in-place sorts, bubble sort, selection sort, insertion sort. We looked at non-adaptive and adaptive versions of them. Counting sort is something that's coming up. We're out of time for the regular lecture here. I would ask you to please come back after this and check out counting sort, because I'm going to go ahead and tack that on at the end here. We saw that some sorts execute more quickly in special cases, and we learned a lot about it. One of the things that I have a lot of fun doing when we're in person is checking out sortingalgorithms.com. Go there. It's a great way to come up with computer science-based party games. Go check out sortingalgorithms.com. You can visually see how sorts run side by side, how insertion sort works compared to selection sort, how that works compared to bubble sort, how it works with a large number or a small number. So check that out, and that's going to be our sort of wrap up here for sorting performance and our elementary sorts. Up next, I'm going to continue into counting sort, and like I said, if you've got to go to another engagement here at noon, jump off, but do come back and catch the rest of this lecture. Counting sort will be on the exam, and it's something that you need to know. We've just run out of time on this particular slot. So counting sort is a special kind of sort. It's a sort that is useful when I have a limited number of keys. So general purpose sorts like insertion, selection, bubble sort can sort anything. Numbers ranging from any input situation here. But an accounting sort is something that I use when I've got a fixed number of keys. So I might use this on sorting an entire classroom into class level. So how do I sort into freshmen, sophomores, juniors, and seniors? There, I've got 4 different keys: freshman, sophomore, junior, and senior. And so that's where counting sort is good. Here in the example, I've got some letters A through G, and I've got a collection of various copies of them, all scrambled up. And so in a counting sort, what I do is I make a pass through the data to figure out how many of each item I have. So this will be the same thing as saying, first thing we're gonna do is count how many freshmen we have, count how many sophomores, how many juniors, how many seniors. Then I'm going to sort of figure out where they belong, right? So if I know that there's one A, for instance, I know that any B that I see should start in position 2. So that's what the counting sort does, is it goes through and first totals up the number of them. And so you see in this example here, there's 1 A, 2 B's, 1 C, 3 D's, 0 E's, 4 F's, and 2 G's. So that's my first pass. I've run through all of the data in a linear amount of time and totaled up how many of the independent ones that I have. In the second pass, I'm going to compute the offset where the keys begin. So the first key obviously begins at 0. That's pretty simple. That's why it starts at 0 there. But since there's 1A, I can tell that 0 plus 1 is where the B's begin, right? And so I can look back and see that there's 2 B's, and since the B's started at 1, the C's have to start at 1 plus 2 or 3. With 1 C, the D's start at where the C's start, 3, plus 1. The D's start at 4. So in that second pass, I figure out where they go. And then in the third pass, I make a full copy of all of these data. I say, well, I write that first D into the position at 4. I'm going to write that F into the position at 7. I'm going to write that B into the position at 1. That G goes to 11. That A goes to 0. That F now doesn't go to 7 because I already wrote an F there, but it goes right after that. It goes to the position 8. And so on. This is how I end up doing a counting sort. So I've got a linear pass to count them all, a linear pass to set up my offsets, and then I've got a linear pass that copies things to exactly where they belong. And I've got a full copy because I've got my unsorted data and I've got my fully sorted data. So I put these things into an output container that are now grouped by key. And you can think of how this might work in a classroom. I say, well, I've got this many freshmen, so I've got 4 rows reserved for freshmen. I've got 3 rows reserved for sophomores. I've got 3 rows reserved for juniors and 1 row reserved for seniors. Then as I encounter a person, I say, well, you're a freshman, go to the first available freshman slot. You're a sophomore, go to the first available sophomore slot. You're a senior, go to the first available senior slot. Another senior, second senior slot. Another freshman, go to the second available freshman slot. And that's what a counting sort does. So it's a very specific type of sort that can only sort a fixed number of independent keys. It can't take any general data and sort it because it doesn't do a whole lot for separating the freshmen. All of the freshmen are together, but they're in groups. All of the sophomores are together, and there's no sort between them. I don't have sorts within that particular class unless I perform an additional sort on that particular class. So here's how it might look. Here are the data all set up, and I'm going to run through a first pass. And in my first pass, I'm going to count all the values. Each one of those things does an increment, and when I get done, I see here that I've got 1A, 2Bs, 1C, 3Ds, 0 E's, 4 F's, and 2 G's. My second pass goes through and figures out where those offsets begin. And so I can see I've got 1A at the beginning, and then I've got space for 2 B's, I got space for 1 C, and it works all the way across. Now, in my third pass, I'm going to just take the data and write them where they belong in my output set. After that pass, now all the data are sorted, and I've got a full copy, but it's sorted. So if I want to return that, I might have to do a swap or do something with my original data, because I have definitely made a full copy to get this done. Counting sort can only be used when I've got a small number of keys, and the range in them has to be limited as well, right? So if I wanted to sort by birthdays, that would be easy to do. 366 birthdays is not a large number. Or if I want to talk about class standings, I talk about 4 or maybe even 5 if you had grad students. Not a problem there. What's not limited is int max. Yes, int max is a constant, but it is not limited. It also changes with architecture, and since I have to have what we call a bucket for each one of these things, I have to have a bucket to total how many of these things were 0, how many of these things were 1, how many were 2, how many were 3, 4, 5, 6. I have to have a bucket all the way up to int max. So I've already got a whole bunch of information there, and if I've got an 8-byte value keeping track of my total in that bucket, I'll end up with 2 to the 64th 8-byte integers, which the reason why we can't use counting sort with int max. I end up with 144 quintillion bytes, or something that would take me 160 million 10 terabyte hard drives just to hold my total counts. You can't use int max as the total number of keys in a counting sort. So don't think that you can. You have to have some small constant number of items. Int max, constant, not small. Here's an example of how it works. We've got counting sort. We'll see that a vector of students is passed in here by reference in line 1, and we declare another vector of students in line 2 that's the exact same size. So there is our full copy. We've even named that vector work copy. So we're going to write all of the students that we have as copies into work copy, and at the very end here in line 13, you'll see we swap students with work copy. So to anyone outside of this function, it feels like I passed in students, they came back sorted, but it did not happen in place. It happened in a copy, and they were swapped out. In line 3, we've got our buckets, right? And here, so how many counts we have. In the case of talking about freshmen, that's going to be 4 different classes, or 5 if we want to say max includes grad students. We run through our first pass, goes through all of the students, and adds a 1 for everything that they see in a particular class standing. So as we see a freshman, we added the freshman. As we see the sophomore, we added the sophomores, and so on. So now I've got this container, which we call counts, that has the total number of freshmen, total number of sophomores, juniors, seniors, and so on. Second pass goes through and gets those offsets just by adding, and we end up by adding counts I plus equals counts I minus 1. So that gives me my base, and then I've got my absolute positions. The third pass goes through in the for loop, and for every one of my students, it copies them into work copy and then updates where the next student should be added here. That's what this counts minus thing does. It tells me where to put things. All right, so that is counting sort. Understand it. It's a good sort to understand. It's not commonly used, but it does have its place, and when you need it, you need it. It's a distribution sort, however, that's important to remember. We talked about our previous elementary sorts. Those are all comparison sorts because I'm comparing individual elements to other elements. Now a distribution sort says, well, I'm going to all of this particular type here, all of that particular type there, and so on. So I don't ever compare any 2 freshmen to each other. I just say you are a freshman, you belong in the freshman row. You are a sophomore, you belong in the sophomore row. I never have to look at two sophomores. So there's no comparison. This is a distribution sort. The time complexity here is now linear in the number of items and buckets, the total number of students and the total number of classes. So that n plus k is what's going on there, because I have to have the n countings and I have to have the k sort of summing to figure out where those buckets began. So the space complexity ends up being a big O of n plus k, because I've had to have a full copy of n items and I have to have the k size to keep track of my counts. It's stable, and it's similar to and often used in radix sort, which is one of our high performance sorts that we mentioned that we won't go into. Do take some time to peruse the radix sort page on Wikipedia to get an idea of what's going on there. That's counting sort. And the last thing that we have to talk about is standard sort. Standard sort used in the STL, and this isn't really much more than what you could find out by doing some documentation check, but it's a good way to give you an overview on it. Standard sort has some parameters, of course. It expects two iterators, a begin and end iterator in STL style with a half open interval, begin pointing at the data with the square brackets, and then end pointing just past good data with the parentheses. The natural sort order, of course, needs to have an operator less than to give me some increasing sort. If there's no natural sort order for the data, like there's a natural sort order for integers, there might not be a natural sort order for stock orders or zombies or whatever, right? In this case, operator less than doesn't work on that data item. So if there is no operator less than available, or if you want to use a particularly different sort, you can add a third parameter to standard sort. So we've got the two iterators, begin and end, and then the third parameter, which is the functor that says, given two of these things, something that falls between begin and end, given two of them, are they in the right order? Return true if this belongs here. If it's false, they should be swapped. The standard sort functor is the one that's used to determine the sort order. So you can assume two parameters, A and B. So if you want an ascending sort, you have to return true when A should come before B, when A is less than B. For a descending sort, you can use the same functor, but you can also reverse the arguments. So this is the case when I want B to be less than A. So I can write that out that way, or I can define my functor in such a way that the swapping happens in the right order. Remember, if these two items are in the right order, the functor should return true. When A belongs before B, return true. When you want B to come before A, you return false. All right, that, as they say, is a wrap. It's time for lunch. We've got a little bit extra lecture here. And there we go. All right.